Welcome back. Today we are going to be implementing A star for pathfinding. And the game map, as you can tell, I kind of advance by tiles here. I can go diagonal. For pathfinding, we'll just be considering the case of cardinal directions, up, down, left, right, or north, south, east, west. There is an enemy down there. I want to be implementing pathfinding between the enemy and myself. So the very first thing we'll do, we have random spawn locations, right? If I spawn there, I spawn there, with the enemy spawning there, I spawn here, I spawn here. I don't even see the enemy. The enemy also has, oh, that's interesting. There's a bug. Oh, I caught a bug. Okay, so we both spawned in the same location. That was actually pretty strange. I thought I had logic to catch that. It's in initialize here. So what I do is I load the map, then I load player and enemies, and then I'll call assign entity positions. And I make a collection of enemies by making an array on the stack, and I set the array's data to a pointer to my singular enemy in the game state. Game state's right here, enemies right here, just a singular enemy. And count to 1 and pass that in. So if we go into map, this is how we bring in operator overloads if you import a file from with a namespace. So I import this math file into my namespace math. Its operator does not get dropped into the top level namespace. I kind of want to check that bug out real quick. Oh, we have map right here. I am saying array unordered removed by value. Now we'll debug that later, but I'll leave a note for myself. So for A star, in the map file, that's actually probably where we'll implement it. Whether or not the enemy will move is selected by some random value. We'll actually replace this. And then the player movement is just tracking input with some cooldown. I'll introduce the resource I'm looking at here. I learned A star, I don't know, like 11 years ago or something in school. I don't think I've ever used it since then. So I had to go brush up on A star. And there's this cool blog called Red Blob Games. Just like a huge wealth of information regarding data structures and algorithms, particularly for 2D games. I'm just going to be cribbing this basically. But we need a priority queue. In the last stream, we implemented a heap with min heap operations available. Oh, I did refactor that. Maybe I should just show that real quick. Modules, SL for standard library. This is where I put it. So we have this test thing here, which essentially will test our ring buffer, test our heap, and then the data structure with a couple operations on it, and then a min heap and a max heap implementation. The heap itself is just what I call now element. And also I made it generic as well, right? So the element takes some generic element type, and then it has a fixed cost, which is an S64 right now. I provide an operator overload for the elements, and here's our heap. So data is now generic, essentially. And then we have initialize destroy. I think I left a semicolon off destroy or something, or maybe that was for the ring buffer in one of the streams. And then we have left and right. And so the min heap is going to be the stuff that we implement previously, min heapify, build min heap, whatever. I just moved it into this file. And max heap is basically the same exact thing I copied, except I replaced reference to min and minimal and whatnot, and also comparisons, such as this used to be less than, just make those greater than. Maybe there's a, I don't know, trickier way to do it, but it's not that much code. It's just like 100 lines. Half of it's like comments, maybe a third of it's comments or so. So coming back here, we need dictionaries, or at least to implement the algorithm as shown here, we need dictionaries. Jai provides a table, I think they call it. Graph.neighbors, in our case, it's going to make the game map.neighbors or something like this. I want to exclude non-walkable space. If I'm right here and I call neighbors, I would get north, south, east, and then west, so up, down, right, left. But I really just want to take up, down, and right. But I would also need to accommodate for trying to get neighbors if I'm a tile right here looking off the map, just cap that stuff. And then we have these dictionaries came from, which provides a mapping of like the key is the destination. So if the key is B and the value is A, what it means is in order to get to B, you can come from A. In our case, these are going to be indices into our tile map. The cost so far is in order to get to a specific location, what is a specific cost from some starting point, and we'll just kind of be computing that as we work through here. The heuristic in my case, I'm probably just going to do Manhattan distance, and so we're left with a data structure that kind of shows how to, not kind of, you can traverse the data structure in a way to build a path from one point to another point. You basically look into goal in the data structure, and you start working backwards from there. Most important question about naming is what should we call it? Like path to, maybe? Maybe like from, I think. From and to. Min heap import file modules sl min heap.jai. So we will take a map. Might as well just take it here, but we're not going to return anything just yet until we implement it. For now, we'll just say heap size is 100. Well, so we'll take U64 for the frontier. We need to take an allocator in here because I don't want to allocate this in persistent storage. Allocator, I think it is. Allocator equals temp. This is going to use the temp allocator from Jai, which is not what I want to use. I actually want to use my arena, pass in the arena here, and just call this a arena. It's actually going to be a pointer to it. I won't do anything with it yet, though. We push start. Start is going to be from. So, and that's from is right now. From is an XY coordinate. So this is a world index to world tile that we need to go the opposite way. We need to go from tile to index. We need to implement that real quick. World index to world tile to world index map. This is going to be tile is a 2f, and we will return, and it is say return a U64, right? I think that's fine. Return the index, world tile to world index. Heap.insert frontier, and then from index and the cost of 0. While frontier.size is greater than 0, we call this current. This is going to be subtract min on frontier if current equals, not really current, right? It's current.e, I think I called it. E is something of element type. So if this is the same as 2, this is where we're going, then we break. And otherwise, we have a for loop. The question we need to ask ourselves, since we're trying to be careful with our memory allocations, is do we set up static storage of just 4 elements for graph.neighbors to write into, or does graph.neighbors return on the stack? We'll just like call this thing here. We need to manually assign the positions here. So player pause gets 5-5 perhaps. The enemy will get 10-10 or something like that. The arguments call site types are a U64 and a vector. Oh, right. For example, to index is world tile to world index m2 to index. 4 U64s on the stack. That's not really a big deal. In fact, we could, yeah, I don't know why I'm thinking about like allocating or whatever. Just pass this on the stack. It's not that big, especially with these small indices. But the whole 4 thing bothers me. I think we pass a view. We don't want to pass a view back, right? If we pass a view back, then we have the typical data on the stack. This is going to get popped. A view would be nice, but the view would point at storage that we don't own. We could take in space for storage here, and then return a view over the input. Again, this is just hack names right now. This guy here, just for U64, which is uninitialized. We don't really care about that much. We take an array view here, and we're going to return an array view. So for neighbor and neighbors view, that's what it is. What is graph? So what I'm looking at here is this line. What is graph.cost? Because we have a heuristic here, and that's going to be the Manhattan distance. This, I see, this is a traversal cost. This is actually going to be 1. This is going to be 1 for everything in my current graph, because I don't really have any terrain costs or movement costs or anything like that. We need to convert the tile back to XY because it'll be much easier to look at neighbors by bumping the X value and the Y value independently. And this is going to be world index to world tile. This is the permutation of movements that we would do for the neighbors, but we need to actually make sure that up, down, left, and right are movable. Minus like negative checks, like for example, if X or Y are negative, you can't move there. I probably should just add those into here, so that way all the call sites of arbitrary positions don't have to do the check themselves. So we'll just test all these essentially. Set end count to 0, and this is what I do here. If we can move to up, Then n data and count is up, and then n count plus equals 1. X needs to be less than the width in tiles, y needs to be less than the height in tiles. That seems to be fine. Okay. The heuristic is going to take, it's actually better to process as vectors because we're going to be taking the xy delta of these things. Okay, there's a whole lot of conversion going on here. After I finish this, I can go back through and try and minimize the conversion between this and that. Okay, we're computing the heuristic between 2, which is a vector, and u64. So let's return a u64. Okay, we'll take in a, is a math vector 2f, and b 2 math vector 2f. Wait, what is this like a constraint? Yo, float. Oh, I think these are constraints. I wondered if we have these. I wonder, yo, do we have constraints? We have return math abs of a.x minus b.x plus math abs of a.y minus b.y. Heuristic of it, world index to world tile of it, and then we pass in to vector 2f. We expect a semicolon. Oh, right. This is going to be is it a dot? How does that work? Yeah, it is a dot. And here we have type mismatch. I wanted a U64, but you gave me a vector 2f. Right. I keep forgetting that. Yes. So this is going to be, yeah, we are converting back and forth a lot. So we got that compiling now. So this all works, but we need to come back here. Let's look at hash tables, I guess. Because the table can never be full. Uh-oh. Why can the table never be full? Yeah, the table can never be full thing is the kind of thing that makes me weary, because if I want to use my own temp allocator and this thing does like a realloc, we'll quote Charles Bloom. What did he say? The last time I looked at hashing, oh, he said a lot of things. Okay, probably interesting to read, but not our business right now. The table. Okay, so we make a new table with a key type and a value type. We'll let it use its own hash function because we had just built-in, we're going to use built-in types for the keys and values. And the given compare function, same thing. There's an entry with a hash, a key, and a value. Came from is going to be a hash table. And we have a key type and a value type. The key type is U64 and then a U64 because we're just dealing with tiles. Init, yes. Slots to allocate. Okay, so how does this work, right? Yeah, internal resize memory. Okay, putting this in our own temporary allocator. See, the allocator that I wrote does not do any. I think it has realloc. It has realloc because I was trying to use my stuff in STB, like STB image or something like this. Yeah, so I have a super naive realloc, right? I basically conform. I satisfy the docs for malloc3. Like a realloc here does a mem copy, basically. All the edge cases aside, it just does a mem copy. But we don't free though. That's the thing, right? Because do I still have free? I got rid of free. We don't free. So a realloc gets more memory to use, but it also it doesn't free the other backing storage. And so it kind of, depending how many times we realloc, it can kind of blow up temp. But we're using the Jai allocator for now, so it's no problem. We'll just proceed. We'll just get it working, and then we'll figure out the memory layout stuff later. So, but we do need to init it, right? And we need slots to allocate. Dude, I don't know. Let's think about this. I mean, we can also just get 100, right? I think that's fair because we're using 100 for the other. Oh, do we have was it return a bool or something? It doesn't return anything. It just assumes. So it came from and then table size. I need to remember somehow to not call dinit if it's my allocator. Allocator is temp. And now we also need a cost so far. And a cost so far also is going to be spec'd out as a probably U64, right? U64. So next thing we need to do is actually just implement the loop here. And then basically just run it and make sure it doesn't barf itself. Okay, so I'm just going to call it once. I'm just going to call it once and initialize. Initialize only runs when we are setting up our memory initially in the first pass-through game update. I just want to make sure we pick good spawn points. That's all I care about right now. This still failed because tinted free with default allocator. Oh, no way. Wait. Do I have to set up the context here? It like remembers, it does like with the remember here. Like remember allocators, basic remember allocators table. Oh, okay, so I need to implement the remember allocators trick thingy. We don't actually need to do that. We don't need to implement that because remember for the heap, we are initializing in, oh, this is the Jai temp allocator. Yeah, so when we use my arena, we won't have to worry about de-initting. So for now, we'll just do this. And okay, so we're at, oh, the camera did not snap to us. We set the camera here, but we set the player position here. Okay, so 5, 5, and 10, 10. That's good. So this guy should make a straight line for us by the time we finish the implementation. Why would this try to extract when a heap size is -1? Or like a certain index. Yeah, no, extract index some index -1. Oh no, we do need to do a table add, actually. We need to do this guy here. Came from start is none. Oh, I don't support nuns. I don't support nuns. What? The reason the none is important here is because when you rebuild the path, you're going to be going back through the dictionary from goal and building, like finding breadcrumbs trails, so to speak, all the way back to something. And in order to know that you've hit a leaf in the trail or a dead end of the trail, or a terminus, I should say, a terminus, you find none in there. Hash table add so far from index, and then 0. If I do S64 to be able to use -1 or something like that, then every time I take a value out of the table, I'm going to have to check, like, is it negative before I cast to U64 and all this stuff. All right, I'll have to spend a little more time thinking about that. You need to pay attention to success, because if it's false, the return value will be uninitialized. See the note on table, find pointer about collisions and about why table is being passed by pointer. We now take table by pointer so that if count collisions, we can modify the collision count, which is stored on the table. Okay, if we stored it elsewhere, this would no longer be necessary, but that might be slower. Okay, all right, that makes sense. So assuming this is the only thing that, yeah, I mean, you can see right here. Well, I don't know what any of these other calls in the table do, but assuming this is the only thing that modifies or mutates our table, passing by pointer does not concern me that much. Let's call it current cost, and okay is hash table find cost so far, and current is going to be .e, I think, because current comes from extract min from the frontier, which in fact we can hoist out of this scope. We don't need to compute that or look that up every single time. So we don't actually have terrain cost or anything like this. So the new cost is going to be current cost plus 1, single tile movement cost. So if we haven't seen this before, if we haven't tried the traverse to this node before, or if we have, but we found a shorter path, then we need to update the table. Okay, my names are all salad here. If exists, and next cost hash table find. The tables are U64, U64, yeah, so it. So if it doesn't exist, we haven't been there before, or if we found a shorter cost, or a smaller cost, hash table add cost so far. And the key is going to be next, which is it, the iter, and then new cost. Priority is new cost plus heuristic. Insert in the frontier. What are we inserting? We are inserting next with priority. It's just it. And lastly, we say hash table add of came from, or to came from. And we are adding next, it's U64, so it, and then current.e, I think. All right, does she build? She does not build. Why? Hash table add. It's called table add. That's why. And then we got some more issues. Priority, number signedness mismatch, type 1 at S64, type given U64. Why? Oh, redeclaration of OK on 300. Yeah, boom. All right, and now it should still die, right? We get a stack trace right because we have an access violation on the min heap there. Okay, cool. So we've implemented the stuff that we need for this guy so far. Next up is just debugging, and then it's running and verifying that I'm actually manipulating the data correctly, inspecting the data structures that we build. And then if everything looks good, what we can do is build, we can, again, traverse over came from, and we can build a path from a reverse path, I think, from, well, we have from and into, so it doesn't really matter which direction it is. We're going to get a path, and then depending on whether we want the player to move or want the enemy to move or something like that, we'll just take one of the either ends and advance that one step essentially on the map. And that's the work for today. Thank you for tuning in. See you next time.